Hello everyone, this is Piero from Stanford University, and today I'm going to tell you about Ludwig and how you can use it for training state-of-the-art NLP models. First, what is Ludwig? It's a deep learning experimentation toolbox. It is based on TensorFlow, and the main interesting thing about it is that it doesn't require you to write code in order to train and use deep learning models, in particular deep learning models for NLP tasks. These are some statistics about it. It's passed 6,700 stars on GitHub. There's a lot of people downloading it and using it and contributing to it every day. And this is a set of companies and institutions that are using it or that we are collaborating with. So the main design principles behind Ludwig is, first of all, I wanted to make it like a general toolbox. So I created this data type abstraction, and I'm going to tell you about, that allows the toolbox to be used for several different tasks. Also, I wanted to make it flexible so that both expert users and novice users can find value in using it. Also, I tried to make it extensible because every day there's a new deep learning model that is proposed by a different researcher that pushes the state of the art, and so the extensibility allows to integrate new models easily. I also tried to make it understandable by providing a set of visualizations that allow to compare models and in terms of performance and in terms of predictions. I also really tried to make it easy to use, and there's both a command line interface and a programmatic API for that. And finally, it's open source, it's Apache licensed too. So I invite you to participate in the community and help contribute and improve it. Let's start with a simple example. Let's assume that we have some text data where we have some piece of news and some classes, and we want to train a model that once we get a new piece of news, we want to have a prediction of what class it belongs to. What you have to do in Ludwig to do that is you have to launch the Ludwig experiment command, providing the data, in this case, the data underscore CSV, and providing a model definition, which is actually the core of Ludwig. The model definition is a string in this case, but can be also provided as a file. And it contains input features and output features. Both are lists, and input feature, you have to provide the name, news, which is the name of the column in your data, and the type text. And for the output feature, you have to provide the name class, which is, again, the name of the column, and the type category. What Ludwig does for you is that it takes the data, splits it in training, validation, and test, but you can also provide your splits already, the data already splitted. And then it trains the model on the training set by validating on the validation set, and finally produces some predictions on the test set and some evaluation on the test set. After the first epoch, this is what you would see. For all the splits, you have loss, accuracy, it's at K. At the fourth epoch, we reach peak validation accuracy performance. And then after a few epochs, there's early stopping because the performance doesn't improve on the validation set. At the end, some predictions are produced on the test set and compared with the ground truth to provide some evaluations. These are some overall statistics and metrics of this evaluation. And these are some per class statistics of this evaluation. So this is basically Ludwig in a nutshell, but how does it work under the hood, and what else can it do other than just training text classifiers? So the way it works at training time is that there's some data that is provided by the user. It's preprocessed, and both some mappings are saved and some preprocessed data is produced. The mappings will be used later for mapping new data, test data, in the same shape of the data that it was trained on. So the preprocessed data is then provided to the model training, and the model training saves both weights and upper parameters. At prediction time, new raw data is provided, and it is mapped into processed data using the same mappings obtained at training time. This preprocessed data is then provided to the model that is loaded from the weights and the upper parameters obtained before, and the predictions and scores that it produces are then post-processed using the same mappings to obtain the final predictions. And the experiment command that I showed you before basically performs first training and then prediction. And in addition, it provides you with training statistics and test statistics that, together with final predictions, can be provided as input to a visualization component that can produce graphs for understanding the model and its performance. So under the hood, what happens is that the magic, first of all, lies in three different things: data type abstraction, and I'm going to show you some examples of that, the declarative model definition that you've already seen an example of, and the smart use of KVRs, which in Python is a way to provide parameters to a function through a dictionary. So if we go back to our example, this is the model definition part. This actually overrides some default model definition and becomes this thing that seems big and scary, but actually I will go through it and explain every single part so that it doesn't look that scary. It's divided in 5 different sections. The input features and output features we've seen an example of. There's also a combiner, a training part, and a preprocessing part. So let's start with the inputs, combiner, and outputs. Why do we need this architecture? The idea in Ludwig is that you have different data types for inputs and for outputs. For instance, text, category, numerical, binary, sequence, vector, set, bag, images, time series, audio, H3, which is geospatial indexing, and date. And by combining the inputs and outputs, you can obtain many different machine learning models. For instance, if you have text as input and category as output, we have a text classifier, as we've seen before. But if you have images input and text as output, you have an image captioning system. If you have category, numerical, and binary as inputs and numerical as output, you have a classic regression system. Or if you have speech as input and binary as output, you can have a speaker verification system. And finally, if you have text and image and binary as output, you can have a visual question answering system. And you can imagine how combining all these different types for inputs and outputs can lead to many more tasks to be solved with Ludwig. In particular, each input can have multiple encoders and each output can have multiple decoders. In particular, for text, we have stacked CNN, parallel CNN, stacked parallel CNN, RNN, combination of CNN and RNN, and transformers. In order to use each of these encoders, in your model definition, you just have to change the encoder keyword to be the encoder that you want to use, for instance, parallel CNN, and also the level at which you want to work, if at the word level or the character level. For transformers, it works at the word piece level. And each encoder has many parameters here, for instance, the number of filters, the fully connected layers, the activation, and so on and so on. And you can change all of them, but you don't have to. Those are provided for you by default. And when I was telling you about KVRs, as you can see, all the parameters that you put in the model definition ends up being used as the parameters of the init function of the ParallelCNN class. So there's a one-on-one mapping between what you provide in the model definition and what is used in the code. And if you have a different encoder like a stacked CNN, you can just provide it by changing the encoder parameter to stacked CNN, and all the other parameters can be changed accordingly. Or if you have an RNN, for instance, you can see that parameters are different. Here you have bidirectional, or the number of layers and the cell type, which could be RNN, LSTM, and so on. So depending on the encoder that you use, the parameters can change. There's many more data types, and if you're interested, I invite you to look at the documentation of Ludwig to understand how it works. But assuming that you have multiple encoders, you need a mechanism to combine the information from all these encoders. And there's many ways in Ludwig to do that. The most simple one is the Concat combiner, which takes the output representation of all the input encoders, combines them by concatenating them, and passes them through fully connected layers. And these fully connected layers are parameterized by all these parameters that you can provide if you want. Then depending on the type of the output, you can perform a different task. For numerical features, you can use them for obtaining numerical predictions, or for doing regression. And you can change the loss and all the other parameters if you want. Binary features are used for doing binary classification, and those are trained using cross entropy. And category features are used for doing multi-class classification, and those are trained by softmax cross entropy. And again, you can change all the parameters of the loss and all of the layers that are involved with this category feature decoding. Set feature decoding is used if you want to perform multi-label classification. And so these are trained by sigmoid cross entropy. And vector features decoding is used if you want to perform, these are really useful for weak supervision, for instance. And those can be optimized by both mean squared error or cross entropy. Finally, the most complex one, output feature that is provided by Ludwig at the moment, is the sequence feature decoding. It could be of two types of decoders, the generator and the tagger. The tagger is, assumes that the input is a sequence itself or a piece of text and provides a tag for each element of the input sequence. For instance, for text, you can tag entities in the text. The generator, on the other hand, can take any input and generates the output one token at a time in an autoregressive way, which means that each token that is generated is used as input to the next step of the generation up until an end of sequence token is finally generated. This is useful for instance, machine translation tasks or any task where you have an input which is of a different length of the output. The training section of the model definition allows you to modify many parameters of the training loop. For instance, the batch size, the number of epochs, the early stopping, the optimizer and its parameters, the learning rate, and so on and so on. And the preprocessing parameters allow you to modify how Ludwig preprocesses the data, and that depends on the different type of the data that you're providing. For instance, for text, there are these parameters that tell you how long, with the maximum length of the sequences, how to tokenize the sequences, and the format in how you want to obtain it in characters or in words, etc. Recently, for text, I also added support to tokenizers using spaCy, which basically means that you have tokenizers that work in all these different languages. So let's look at some example models. This is the one that we've seen at the beginning, where you have news as input and class as output, and this allows you to perform text classification. As you can see in the model definition, you have a list of input features with only one element in this case, which is the text named news. And here we're using, for example, an encoder ParallelCNN of level word. And the output is name, class, and type category. This is another example where you have a simple sequence-to-sequence chit-chat dialogue model, and you have sentences uttered from a user 1 and answers the following sentence provided by user 2. And so given the sentence from user 1, you want to predict the sentence from user 2. The way to do it in Ludwig is you provide the input name user 1 and type text, and you can use any encoder. In this case, we decided to use an RNN with cell type LSTM. And for the output feature, you have, again, only one output feature. The name is user2, the type is text, and the decoder here is a generator, because obviously, you know, the length of the input of user 1 and user 2 may be different. And the cell type, again, is LSTM. And here we set the attention mechanism to use but now attention. This is an example for text tagging. It can be used for doing name entity recognition, part of speech tagging, and many other tasks that require tagging. This example is with name entity recognition. Given a sentence like Blade Runner is a 1982 neo-noir science fiction film, etc., you have to provide a tag for each element of the input. So for instance, Blade is tagged with movie, Runner is tagged with movie, is A are tagged with like dash, or if you want O, if you use IOB tagging, and so on and so on. And so each single output tag is associated with one input element from the utterance. In order to train a model to do so, in Ludwig, you just have to specify the output feature to use a decoder tagger instead of the generator. And that's all you have to do really for obtaining these predictions. Another example that is another NLP example is summarization. It's very similar to the previous one. This is a kind of extractive summarization where you basically tag from a sequence, in this case from an utterance, the elements that you want to keep and the ones you don't want to keep. And so when you give it a new sentence, you will have a prediction which is a sequences of ones or dashes or zero, whatever you want, which basically means the ones are the words to keep and the dashes or the zeros are the words not to keep, to filter out. The model definition for this task is exactly the same as the previous one, just the name of the column in this case is keep, and so you have to specify name equals name keep in the model definition. But the architecture that is going to be trained in this case is exactly the same. Another useful example of what Ludwig can do is natural language understanding. As you can see here, you have an utterance as input, and what you want to produce as output is a frame, and the type of frame is defined by the intent. In this case, it's like flight booking. And the tags that you are tagging the text with are basically the slots of the frame. For instance, if you have the slot flight, you may want to fill the city where you're flying from, the city where you're flying to, and at what time you want to fly out. And so in this case, you will see that Boston is tagged as city, and 8:38 and PM are tagged at time. And so these tags can be used for extracting this information from the utterance. The way to train a model like this in Ludwig is by providing one input feature, again, utterance of type text, and encoding it any way we want, for instance, with an RNN with cell type LSTM. And then for the output features, we can specify more than one because we want to provide predictions for the intent and the tags at the same time. And so the first element of output feature as name, oh, sorry, there's a typo there. It's not IOB, it should be tag, but of type sequence, and the decoder is a tagger. And we also have another element in the list of output features, which is intent, which is type category. So Ludwig, what it will do, it will train a model to predict both outputs in a multitask fashion, so optimizing both tasks at the same time. So now we've seen many examples of how you can use Ludwig for doing many different tasks, but how can I actually use it? It's very easy to install, just pip install Ludwig. And then we have seen many examples of command line commands, but there's also an API that you can use very easily for training and using Ludwig models. All you have to do is to import a Ludwig model class from ludwig.api, then instantiate an object from this class with a model definition, which is exactly the same model definition that we've seen up until now. And now that we have a model object, we can train it on some data. We can save it if we want. We can reload it if we have a model that we have already trained, and then we can use it for prediction on some new data. Once you have a model trained with Ludwig, you can also spawn REST API by calling Ludwig serve and the model path of the model that you saved. And then you can query it. So it's very, very handy. As I told you before, there's also a bunch of visualizations that Ludwig provides for you. In particular, when you run an experiment, what you obtain is a trained model, some predictions in CSV format, some probabilities in NumPy format, and statistics of training and test. And also, while you're training, because it's a TensorFlow model, while you're training, you can actually use a tensor board to visualize what's going on during the training. So from these files, what Ludwig can provide to you is a set of more than 20 different visualizations. Here we have a subsample of those. For instance, the first compares two models from 3 different measures. The second one is a calibration plot. The third and the fourth one are plots that compare coverage against accuracy. The fifth one is a visualization that compares the predictions of the model. And the sixth one is a comparison of the frequency of classes against how accurate is the model of those classes. But there's many, many more at your disposal. I can suggest you to look at the documentation. So we are on the verge of releasing a new version of Ludwig, version 0.3, that introduces many new things that are useful, in particular, many new things that are useful for NLP. So let me briefly go through them. There's many features. The most interesting one actually are these ones. So the first one is we are integrating with Hugging Face transformers. And so what this will enable you to do is to provide encoders. So for instance, the keyword encoder can be used to call and import one of the different transformers model from the library. So for instance, you can import BERT, you can import DistilBERT, you can import T5, Electra, GPT-2, and any other model that is available in eigenphase transformer, or you can also provide your own model trained with eigenphase transformer. This is very useful because this basically allows you to train a classifier or any other kind of task on top of these models that are state-of-the-art without writing any code at all. You just have to specify encoder Electra, for instance, and you have a state-of-the-art classifier. Another interesting thing that we added is hyperparameter optimization. So let's assume that what you see on the left is the model definition of your model. This is YAML syntax. And as you can see, there's an input utterance of type text and an output class of type category. And there's some training parameters like the learning rate and the type of the optimizer. What you can do is you can also specify this hyperopt section in your model definition, and you specify which metric you want to optimize and which parameters you want to optimize. In this case, we want to figure out what's the best cell type to use, what is the best learning rate within a specific range, and what is the type of optimizer between a set of type of optimizers. You can also specify how to sample the new, the different hyperparameter configurations, and you can do grid search, random search, and you can also use PyShot, which is library for doing Bayesian optimization. And you can also specify how to execute it, if you want to execute on your machine serially or in parallel, or by using Fiber, you can run in parallel on a cluster of Kubernetes machines. You can also train in a distributed way by using Horovod, with adding the command Horovod run and the number of machines and resources that you can specify with all the Horovod parameters, and then the use Horovod flag in Ludwig so that it knows that it has to use Horovod for training in a distributed way. This helps a lot because Horovod allows you to scale almost linearly with the number of machines that you're providing. Also, I was telling you about the extensibility of Ludwig, and this is an example of how extensible it is. This shows how to add a new custom encoder for text and for, actually this is for images, not for text, but for text is basically exactly the same thing. Assuming that you are a researcher and you created a new layer or a new encoder for a specific data type, what you can do is you can create a class that extends TensorFlow 2 layer class. And in the init function, you can provide all the upper parameters that you want to expose in the Ludwig model definition. And in the call, what you actually do is you just have to obtain the inputs and if the model is training or not, and potentially a mask. And then these inputs will have a specific size depending on the type. In this case, we're seeing images, and so we expect batch times height, width, and channels. But if this was a text, you will have batch times length of the sequence. And then you have to provide the output in a specific shape. In the case of images, it's batch, new height, new width, and new channels. In the case of text, it will most likely be batch, sequence length, and hidden sides of the last layer. If you conform with this structure, so providing tensor as input and tensor as output, you can put inside whatever code you want for your encoder, and then this will be available directly in the Ludwig model definition for you to use. So this was an overview of everything Ludwig, and an example of many different NLP tasks that can be attacked with Ludwig, and how you can obtain state-of-the-art deep learning models using it. If you're curious, I suggest you to look at the documentation at the website ludwig.ai. There's also the repository on GitHub that you can play around with. There's a couple blog posts, a white paper, and many more resources on the web. Feel free to explore. And this is also a list of key contributors that helped me a lot in developing Ludwig so far. I really want to thank them because thanks to them, Ludwig is growing and improving day by day. Thank you so much for your attention. We'll take questions now.